going to talk about the kernel and range of linear transformation. Kernel and range of a linear transformation. Let us have our definition. A linear transformation, let L be a linear transformation. A linear transformation L from V to W is said to be one-to-one if we take two elements from two different elements of V, if whenever we take two different elements of V, L of those elements will be different. If for all V1 and V2 and V, where V1 does not equal to V2, that implies that L of these objects, L of V1 and L of V2, are different. If you start with different elements from V, then L of those two different elements will be different. L of this element and L of that element, V2, are different. Okay, I don't like that definition personally. Alternatively, now, let's see what we have. We have V1 not equaling to V2 implies that L of V1 does not equal to L of V2. We can do the contrapositive. We can negate this. That is, if this statement is not true, if those things are not equal, if these things not being equal to one another is untrue, well, that means they are true. And for contrapositive, we put them first. Implies the negation of this. If it is not true that V1 does not equal V2, well, then V1 equals V2. I mean, there's two alternatives. Either V1 and V2 are equal, or V1 and V2 are not equal. If it isn't this one, well, then it's that one. There's only two reasonable possibilities. Either the two vectors are equal or they're not equal to one another. Okay, I want to just not put that in brackets. Alternatively, L of V1 equals L of V2 implies V1 equals V2. This is another way of thinking of one-to-oneness. And that's usually the way I'll do it. I use the alternate definition. They're exactly the same. So, suppose I give you the following linear transformation and I ask, is it one-to-one? Let L from R2 be a mapping from R2 to R2, be a linear transformation defined by the following. L of something in R2, call it xy, it gives you something back in R2. Say x minus y, x plus y. Now, okay, so the question is L 1 to 1? So I take L of two things, and I say they're equal. And I want to conclude if the two things are equal. L of xy is x minus y, x plus y. And it is equal to L of AB. You know, let us start off nice and clean. Suppose the following. Suppose L of one thing equals L of another thing. Suppose L of xy is equal to L of AB. Then, well, L of xy is, first you do the first minus the second, x minus y, comma, and then you add the first and the second, x plus y. And this should equal to L of AB, which is a minus b, a minus b, comma, a plus b. Now, if these two vectors are equal, their components must be equal. X minus y should equal to a minus b, and x plus y should equal a plus b. X plus y should equal to a plus b. Now, we want to conclude that x is a and y is b, or not conclude that. Well, if I add these two together, I get 2x is equal to 2a, which implies x is a. Well, that's the start. Now, that's if I add these two rows. If I subtract them, x minus x is 0. I get negative 2y is equal to negative 2b. Well, if you multiply negative 2 by different values, you won't get equality. You only get equality when you multiply negative 2 by the same number. So y equals b. Therefore, L is 1 to 1. Therefore, L is 1 to 1. If I take L of one thing and it equals L of another thing, it turns out that those two things are equal. One thing in V goes to one thing in W. L is the linear transformation from V to W. If you take L of one thing in V, you get one thing in W, and nothing else in V. L of nothing else in V will also give you W. What exactly is this saying? It's saying the following. You have the set V, and you have the set W, and L is a linear transformation between the two sets. If this is an element in W, and this element in V gets mapped to that element in W, you cannot have this. You can't have two things going to one. And if it's 1 to 1, and you quote, did have two things going, well, V1 and V2 actually are the same. That is, we're just doing this. We don't have this second distinct element. V1 and V2 are the same. What that means is you have some elements in W, you have some elements in W, and you have some elements in V, and every element of V goes to a unique element in W. Possibly this element goes here, and this last element goes there. But you will not have the case where an element, a different element in V than the others, than these four, will go to, you will not have two things from V going to the same W, the same element in W. If one shows you this picture, you say, no, it is not one-to-one. To make this one-to-one, it's not hard at all. Let it go to this element. Notice, there are some elements in W that have nothing going to them. Nothing in V went to that element in W or that element in W. Again. Now, you can have a mapping and it'll be very, very well defined if everything in V, a linear transformation mapping, if everything in V goes to the same element in W. It's not a function, remember. If something in V goes to do two different things in W, that's not even a function. But it's okay if everything goes to one element. Or most go to one element and something else goes to another element. But this function is not one-to-one. It's not one-to-one. There are more than one element that went to W. There are more than one element in V that went to W. To this element in W. Call it W1. There's more than one element in V that went to W1. You can't have that. To be one-to-one, it means for each element in V, it goes to different for each element in V, it goes to different elements in W. But W might have elements that don't even go to them. This is one-to-one. Let's put down another linear transformation and decide if it is one-to-one. Now, just for the record, if it's not one-to-one, what you can do is you can actually say, look, L of 3, 2 is equal to L of 5, 2. But 5, 2 does, oops, I meant to say this does not equal to. It doesn't matter because none of this came out. If you can show that L of 3, 2 is equal to L of 5, 2, but 5, 2 does not equal to, or 3, 2 I meant to write first, doesn't equal to 3, 2, then L is not one-to-one. You can show a concrete example. Okay. Suppose L from R3 to R2 is a linear transformation defined by L of XYZ is equal to X comma Y. is L 1 to 1? Suppose L of x, y, z is equal to L of a, b, c. Now, L of anything, you just get back the first two values. That is, then x comma y is equal to a comma b. Hence, x equals a and y equals b. But that's not enough. I mean, we have x and a are equal and y and b are equal, but we never concluded that y equals c. But v, it can, but it also cannot. V does not have to equal c. Therefore, L is not 1 to 1. Now, if you notice that the last components don't have to be equal. So here is one argument to show that L is not 1 to 1. Okay. Now what you can do is say L of 3, 4, 5 is equal to 3, 4. And L of 3, 4, pi is equal to 3, 4. That is, L of this and L of that are equal to one another. They both equal 3, 4. But what I'm taking L of in the first case, 3, 4, 5, and what I'm taking L of in the second case, 3, 4, pi, they're not equal. They're not equal. That implies L is not 1 to 1. You cannot show an example to convince somebody that L is 1 to 1. You cannot show it by an example. And I hope the reason is very clear, because the only example that you can use to attempt to show that it's 1 to 1 is you say, look, L of 794 does equal to L of 794. And this is always going to be true so long as you're starting from R3. And, yeah, look at this. 794 does equal 794. Well, of course it does. You rigged it to be that way. If you take L of the same thing, you're gonna get equal. And you're rigging those two things to be the same. So no, you can't do that. Okay, let's look at another definition. Now this section, in my opinion, is very, very beautiful section. A lot of fun. Don't let it be painful. If it's painful, it's because you don't know your definitions and your theorems. Write them down. Memorize them. You know, I said in the past, memorization's not good. Now, somebody can ask me a question, is this theorem valid? And I'll think for a second or two, and I'll say yes. But that doesn't mean that, but I had to think about it. That is, that theorem is not part of me yet. I won't ever use that theorem to prove something or do a problem because it's not in my head. Yeah, of course it's true. Yeah. But unless you can state it on your own without somebody asking you, is this theorem true or is this rule true, then you're never going to use it. You have to have all these concepts in your head. Let L be a mapping let L, the mapping from V to W, be a linear transformation. So L is a linear transformation. The kernel of L is a subspace of V. Well, for now we'll call it a subset. It is a subset of V that consists of all V in big V such that L of little v is the zero vector. Now, you take L as something in V and you get something in W. So that zero vector is in W. I ran out of room. I couldn't put it in the lower right-hand corner. So, if you take L of a vector in V and you get the zero vector, bingo, it's in the kernel. That's the definition. How do you get to be in the kernel? If L of the kernel of V, the kernel of L. If you take L of things in V and you get the zero vector, those things are in the kernel. Okay. Let's look at this example. We looked at it before. L is a mapping from R3 to R2. Is a linear transformation defined by L of x, y, z is equal to x comma y. We want to find the kernel of L. What can you take L of? What can you take L of and get the zero vector? Okay, well, we want L of, say, x, y, z, which we know is equal to x comma y. We want it to be 0, 0. Okay? We want to know what can I take L of to get 0, 0. Well, this implies that x equals 0 and y equals 0. X and y equals 0. That is, if you take L of 0, 0, anything, you will get this comma or that, which is the zero vector in W. Remember, you take L of V's and you get things in W. So we're done. The kernel of L, it's the set of all 0, 0, R or Z, whatever letter you want, I'll use R, such that R is any real number. That's the kernel. It's the things in R3 that have the first two entries being 0. That's the kernel of L. You take L of anything in this form where that last entry, R, is just a real number, you'll get the zero vector. Just remember, L of something in R3 is just the first two entries, x comma y. let us look at another problem. Same exact problem. Find, or same exact question. Find the kernel of the linear transformation. I may not write that L is a linear transformation, but it's understood. Okay, I'm telling you verbally. Let L of that element, which is in R4, equal to this. X plus Z, Y plus W. We want to find the kernel of L. So we take L of an arbitrary entry in R4, arbitrary element in R4, and what you get is the first entry is the sum of the first and third entry, and the second entry is the sum of the second and fourth. But the fourth is W. We want this to be the zero vector. Oh, you mean X plus Z should be 0 and Y plus W should be 0. Okay. X plus Z should be 0 and Y plus W should be 0. Well, that implies that X must be negative Z and that Y must be negative W. So in other words, when you have X, Y, Z, W, it must be negative Z, that's X. Y, I'm just reading here, Y is negative W, and Z is Z, and W is W. That means the kernel of L is the set of vectors in this form. Negative Z, negative W, Z, W, such that Z and W are real numbers. If you wanted to, instead of using Z's and W's, you can use R and S. R and S for the third and fourth, negative R, negative S, such that R and S are in the set of real numbers. That's the kernel. That is, if you take Ella, pick anything you want for the last two, 3, 7. And for the first two, it's the last two, but negate them. This will give you 0, 0. Because when you add the first and the third, you get 0. And when you add the second and the fourth, you get 0. And that's how it was defined. How did you get X plus Z? You added the first and the third. How did you get Y plus W? You add the second and the fourth. Okay, be able to say the definition in words. So at the very bottom, it says what the kernel of L is. The kernel of L is equal to that set. We mentioned, since all these elements in the kernel comes from V, that the kernel of L is a subset of V. Let's look at this last problem. The kernel of L were in R4. That is, they were in V. L is a mapping from R4 to R2. L is, we normally say it's a mapping from V to W. So V is R4 and W is R2. It's in the V set. The kernel is in the V set. So it's a subset of V. Remember, V is just R4. We are in R4. The kernel is in R4 with restrictions. The first and third entry have to add up to 0. The second and the fourth entry have to add up to 0. It's just a subset of R4. But some subsets of V turn out to be vector spaces. Sorry, subspaces. Some subsets of V happen to be subspaces of V. Is that the case here? Is the kernel of V, the kernel of L, just a subset of V, or if you prefer, a subset of R4 in our last example, or is it something more? Is it a subspace of R4? Theorem. If L from V to W is a linear transformation, then the kernel of L is a subspace of V. Now, recall that L of the 0 vector in V is the 0 vector in W. That is, the and since V is a vector space, the 0 vector is in V. That is, the kernel is not empty. A proof. First, note that the kernel of L is not the empty set, since 0 from V is in the kernel of L. L of the 0 vector is the 0 vector. Okay, so now we need to show two things to show a subspace. We need to show that it's closed under addition and closed under scalar multiplication. Let V1 and V2 be in the kernel of L. That is, L of V1 is 0 and L of V2 is 0. But I want to show that their sum is in the kernel. Well, this, by the very definition of linear transformation, L of V1 plus V2 is L of V1 plus L of V2. But L of V1 is a 0 vector in W, plus L of V2 is a 0 vector in W. When you add the 0 vectors in W, and voila, you get the 0 vector in W. Okay. Now, let C be any scalar. Then L of C times V1, well, that's C times L of V1. But L of V1 is the 0 vector. So you get C times the 0 vector in W. And regardless of what C is, you multiply it by the 0 vector, you get the 0 vector. Therefore, the kernel of L is a subspace of V, regardless of what V is. In our last example, V was R4. But in this theorem, it doesn't matter. It's true for any vector space V. If L is a mapping from any vector space V into any vector space W, I don't know if I said L is a linear transformation, from vector space, from any vector space V into any vector space W. But if L is a linear transformation from V to W, then the kernel of L is a subspace of V. Okay. Suppose L from R2 into R1 is a linear transformation defined as follows. Defined by L as something in R2, call it XY, equals something in R1. It equals to just X. Okay, so we have this plus an extra line for some reason. Okay. What I want to do is I want to find not the kernel of L, but the dimension of the kernel of L. Well, first we want to find my goal or the question is to find the dimension of the kernel of L. But first you find the kernel of L. You take L as something and you get back something else. What can you take L of? Well, we want L of xy, which is x, to be the 0 vector in R1, which is just 0. That is, we want x to be 0. Okay, so the kernel of L is the set of all 0, y. Because I was saying it was x, y, but we learned x is 0, such that y is a real number. Now, this is the same as, there's many ways of thinking of it. This is the same as 0, 1 times r, where r is a real number. However you think about it, you just have to ask yourself one question and get it right. To pick something in the vector space, how many values do I have? How many different values must I tell you the values? How many different variables do I have to tell you the value of? Okay, for example, here, if I tell you y equals 7, then you get 0, 7. I have to tell you the value of one variable. Down here, if I tell you r is 7, then you'll get 0, 7. I have to tell you the value of one variable. Now, if the vector space were things like this, say R, S, and R plus S, if the kernel were in the form of things that look like this, what's the least number? Maybe I should have been saying that earlier when I got my 1. What's the least number of values I need to give you? For example, I can tell you r is 3, and I can tell you s is 7, and I can tell you r plus s is 10. But I didn't have to tell you what r plus s is. If I just tell you what r and s is, you can do the addition yourself. 3 plus 7 is 10. That would be dimension 2. In our case, it's dimension 1. The dimension of the kernel space is one-dimensional. I just have to tell you what y equals, or what r equals, or if you want to call it the letter q, I just have to tell you what q is. That is, if for some reason you wrote q here and you wrote q there, either place, here to know an exact value for the kernels, I would have to tell you what Q is. Here, if R was Q, I'd have to tell you what Q was, and you'll have an exact value. That's said to be one-dimensional. You just have to pick a value for Y, and you'll have an element in the kernel. You don't have to pick a value for X. It's been picked for you. The value of X is 0. You do not have to pick a value for X. It's been already chosen for you. Selected. It is the number 0. So let's look at the problem we did a moment ago. L is a linear transformation from R4 to R2. It is defined by the following. L of x, y, z, w is equal to x plus z and y plus w. And the question is, find the dimension of the kernel of L. Now, we established that the kernel of L is a set of vectors in this form. Negative R, negative S, R, S, such that R and S are real numbers. Now, once we find the kernel of L, we can find the dimension of the kernel of L. For you to make this an exact value, an exact concrete vector like 1739, to get it to be an exact concrete element in R4, I just have to tell you what R and S is. If I tell you R is 7 and S is negative 4, well then this vector will become negative 7, negative 4, 7, and negative 4. I just have to tell you what R and S is. If I just tell you what R is, you won't know what goes here and here. Likewise, if I don't tell you what S is, I just tell you what R is, or here I didn't tell you what S is. Right? If I just told you S, but I didn't tell you R, well then you won't know what the first and third entry should be. It's two-dimensional. I have to tell you the value of R and S. I have to tell you the value for R and S for you to be able to tell me what the exact vector is in the kernel. It's two unknowns, R and S. It's two-dimensional. It's two unknowns. Okay. And here's a very powerful theorem. A linear transformation L from V to W is 1-to-1 if and only if the kernel of L is the zero vector. And it comes from V. It's the only thing that gives you, it's the only thing in the kernel, that is, if the only thing you can take L of is the zero vector, to get the zero vector, then it's 1-to-1. This is 1-to-1 if and only if the kernel of L just contains the zero vector. proof. Suppose L is 1 to 1. So we're assuming 1 to 1. I want to show that the only element in the kernel is in fact the 0 vector. We know that the 0 vector is in the kernel of L. Now suppose V is also in the kernel of L. And this is where it all comes together since L is 1 to 1. Then L of the 0 vector is equal to L of V, because they're both in the kernel and they both equal to the 0 vector in W. But L is 1 to 1. But L is 1 to 1. That is, if you take L of two different things and you get equality, we can say that those two different things are equal. Those seemingly two different things are equal. That is, I'm telling you V is in the kernel. But it turns out V is a 0 vector. Hence, the kernel of L is just the 0 vector. You can't take L of two things and get the 0 vector. Not if L is 1 to 1. And all I use is the definition of 1 to 1. So I show that when we start with 1 to 1, we conclude the kernel of L is a 0 vector. Now I'm going to assume the other way. Assume the kernel of L just contains a 0 vector. Now I want to show that L is 1 to 1. That is, if I take L of two different things, those two things actually were equal. Okay. Let V1 and V2 be in V such that L of V1 is equal to L of V2. Now somehow I want to conclude that V1 and V2 are equal. If I do, if this guarantees me that V1 and V2 are equal, then L is 1 to 1. Then, bringing this to the other side, then L of V1 minus L of V2 is equal to the 0 vector in W. But L of V1 minus L of V2, let me not say but, then this is the same as L of V1 minus V2. Oh, and it equals 0. Therefore, this is in the kernel. Therefore, V1 minus V2, is in the kernel of L, which is a 0 vector. That is, V1 minus V2 is the 0 vector. But that implies V1 equals V2. If you subtract two vectors and you get the 0 vector, then these two vectors were the same. Therefore, L is 1 to 1. I'm taking what I initially think is L of two different values. And I'm concluding that those two different values were in fact not different. They were the same. means L is 1 to 1. So I started off with the kernel of L just being a 0 vector, and I'm concluding that L is 1 to 1. Those are the same two statements. If a linear transformation is 1 to 1, then the kernel is a 0 vector. If the kernel of is just a 0 vector. If the kernel of a linear transformation is just a 0 vector, then that linear transformation L is 1 to 1. They go hand in hand. You don't have one without the other. They're the same exact statement. 1 plus 1 equals 2, and 2 minus 1 equals 1. They're the same exact statement. A plus B equals C, and C minus B equals A are the same statement. Either they're both true at the exact same time, and they're both untrue at the exact same time. You don't have one without the other. 2 plus 3 does not equal 7. False. 7 minus 3 does not equal 2. Okay. 7 plus 4 does equal 11. 11 minus 4 does equal 7. 11 minus 4 does equal 7. If 7 plus 4 equals 11. Okay. They're either both true or both false. They're the same statement. A plus B equals C if and only if C minus B equals A. They're the same statement. If you made a truth table, they would look exactly the same. Now, here's a neat thing. We have a consequence of that last theorem. Any two solutions to L of x equals b differ by an element in the kernel. Now, what is this saying? This is saying that if L of x1 is equal to b, and L of a different vector is also equal to b, then it's saying that the difference between the two vectors is equal to something in K. Something in the kernel of L. If you subtract x1 and x2, you'll get K. And whatever that K is, it'll be in the kernel. Okay. Now, consider this. Consider L of x1 equals b, and L of y is equal to 0. Okay? Well then, L of x1 plus y, this is equal to L of x1 plus L of y. L of x1 is b plus L of y is 0. And b vector plus a 0 vector is the b vector. Notice that those two, this vector, x1 plus y, and we'll call that whole thing x2. x2 is equal to x1 plus y, where y is in the kernel. And if I bring this over, then the difference between these is equal to something in the kernel. They both gave us the vector b. L of x2 gives me the vector b, and L of x1. It says L of x1 is b, and L of that vector x2 is also b. So that doesn't mean that there's other cases where they won't differ by a constant. Doesn't mean that they have to differ by a constant by what I've shown so far. Okay. Perfect. Just like I said before, let x1 and x2 be two solutions to L of x equal b. Let L of x1 and x2, let x sub 1, and x sub 2 be two solutions to L of x equals b. That is, L of x1 equals b, and L of x2 equals b. So, L of x1 is equal to L of x2. Then L of x1 minus L of x2 is the zero vector. But the left side is the same as L of x1 minus x2. So, x1 minus x2 is in the kernel of L. Because L of anything, if it equals to the zero vector, then anything is in the kernel. That is, x1 minus x2 is equal to k for some k in the kernel of L. That is the difference between x1 and x2. Two solutions to Lx equals b. Live in the kernel. They differ by something in the kernel. Bringing this to the other side, we have x1 is equal to x2 plus k. These x1 and x2 are not equal, they just differ by k, something in their kernel. So in some ways, there's really just like one solution. If you ignore things in the kernel, whatever that means, L of x equals b just has one answer. Because all the other answers that you may say, well, of course, there's many answers. Well, how do you go from one answer to another? You add something in the kernel. In other words, suppose the kernel of L is equal to K1, K2, K3. There are only 3 elements in the kernel of L. Okay, and suppose L of x1 is equal to b. B is not 0. And then there are other solutions. Other solutions to L of x1 equals b are, it's not another one, but there's x1. Now you can have x1 plus k1, and you can have x1 plus k2, and you can have x1 plus k3. And for a fraction of a second, I was going to say, and that's all of them. But of course not, because the kernel is a subspace. That is, multiples of each of these are also in the kernel. That is, I can also have x1 plus any number times k1. I can have x1 plus any multiple of k2. I can have x1 plus any multiple of k3. But this wasn't the first one that came to my mind when I said, no, it's not just these. I was realizing that if you add these, L of k1 plus k2, for example, well, this is L of k1 plus L of k2. Now, the reason k1 is in the kernel is because L of it is 0, plus the reason k2 is in the kernel because L of it is 0, and 0 plus 0 is the 0 vector. That is, now we can also do alpha b1 plus alpha k1 plus beta k2. Because the alpha can come in the front here, and the beta can come in here, and alpha times 0 is 0. Beta times the 0 vector is the 0 vector. So you can have linear combinations of these. So the list just goes on and on. But all you're doing is adding to x1 stuff in the kernel. From x1, all you're adding is stuff in the kernel. Now, of course, if the kernel just contains 0 vector, then I'm just adding the 0 vector. 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 That is, I'm always getting x1. X1 plus a multiple of k1 plus a multiple of k2 plus a multiple of k3, where alpha, beta, and gamma can be any real number. In fact, it looks to me like that's it. That's it. That's the things in the kernel. Sorry. That's the solutions to L of y equals to b. If you take L of any of this, L of x1 plus alpha k1 plus alpha k2 beta k2 plus gamma k3, well, first you get L of x1 plus you get L of this, which is alpha times L of k1 plus you take L of this, and the beta can come out. Beta times L of k2 plus gamma times L of k3. But the last three terms are the 0 vector. This is a 0 vector times alpha is a 0 vector. I can write it up here. You get L of x1 plus the 0 vector, again the 0 vector, again the 0 vector, which is just little b. L of x1 is b, and you're just adding the 0 vectors. So that's important to know. Once you have any solution to L of x equals to b, and you know the kernel, you can possibly find many other vectors. Unless the kernel is the 0 vector. That is, unless L is 1 to 1, which makes sense. You can't take L of different things to get B if L is 1 to 1. And now let us talk about the range of L. Definition. If L is a mapping from V to W, is a linear transformation, then the range of L, is the set of all little w's in W such that there exists some V in V with L of V equals W. If you can take L of something and get W, then W's in the range. For example, if this is V and this is W, and V has those 5 vectors, and vector space W has these 6 vectors, and this first vector goes there, and the second one also goes there, and the third one goes here, and the fourth one goes here, the fifth one goes here. And these vectors are denoted W1 through W6, W5, W6, and L. The range of L is W1, W2, W4, and W6. Because something went to W1, namely V1 and V2. And something did go to W2, namely V3. But nothing went to W3. But something went to W4, namely V sub 4. And nothing went to W5, but something went to W6. V5, L of V5 equal W6. If you can take L of something and get W2, then W2's in the range. W2's in the range of L. And we were able to take L of something. We were able to take L of 2 different things to get W1. So W1 is still in the range. L can't be 1 to 1 if I took L of 2 different vectors and I got W1, but we're not talking about 1 to 1. We're talking about the range of L. It's the thing, it's the set of vectors in W that have the following property. L of something in V equals those W's. L of V4 equal to W4. So W4 is in the range. But W5 and W3, nothing in V gets mapped to W3. L of nothing in V gives you W5. So they're not in the range. Notice, I skipped W3 and W5. Take a little break. Think about what I'm saying. Okay, it's abstract. There's no numbers, no, just letters. The only numbers you see are subspace. Okay. The range of L, if L goes from V to W, the range of L is a subset of W. If Is it a subspace of W? Answer is yes, it is. If L from V to W is a linear transformation, then the range L is a subspace of W. Okay, proof. The range of L is not empty since 0 is in the range L. Since L of the 0 vector is equal to the 0 vector. I was able to take L of something to get the 0 vector. Okay. Let W1 and W2 be in the range L. Now, how did W1 get to be in range L? Then there exists V1 and V2 such that L of, say, V1 gave you W1 and L of V2 gave you W2. Okay, that's how W1 and W2 came to be in the range of L. I was able to find L of something, whether I called it V1 or not, that gave me W1. I was able to find L of something that gave me W2. Okay, then L of V1 plus V2. See, I want to show that I can take L of something to give me W1 plus W2. Now, this is also in V because V1 is in V and V2 is in V, and V, capital V, is a vector space. Because when you add two vectors in V, you get something in V. For we know, since it's a linear transformation, this is L of V1 plus L of V2, and L of V1 is W1 plus L of V2 is W2. And since I was able to find L of something, they gave me that vector, hence that vector is in the range of L. So I showed that it's closed under addition. The range of L is closed under addition. I took two things in the range of L, and I showed that the sum was in the range. Now we have to do scalar multiplication. Let C be a real number, and W1 in the range of L. Okay? W1 in the range of L implies there exists a V1 and V such that L of V1 is W1. Now, L of C times V1, well, this is in V. This is equal to C times L of V1, which is C times L of V1, which is W1. So I was able to find L of something that gave me any scalar, any multiple W1. So this is in the range of L. Therefore, range L is a subspace of vector space W. Beautiful stuff. So I'll put down a linear transformation and it'll ask to find their range. What is the range of this linear transformation? Is it 1 to 1? What is the range? It's a very simple linear transformation. You want to know what the range is. I even want to know if it's 1 to 1. Let L from R3 to R3 be a linear transformation defined by L or something in R3, call it X, Y, Z, and it's supposed to equal something in R3. Let it equal itself. Okay. Is L 1 to 1? Is L 1 to 1? What is the range of L? Is it 1 to 1? Okay. Suppose L of one thing is equal to L of something else that seemingly looks different. Well, in this case, L is identity mapping. L of X, Y, Z is X, Y, Z. And L of ABC is ABC. Oh, yeah. These two vectors are equal. So L is 1 to 1. Now, what is the range? Which elements can you take L of something of and get something in R3? L of elements give what in R3? Well, let QRS be in R3. This R3. So maybe it has to be that Q and R are the same. That is, to be in the range, maybe Q and R have to be the same. Then L of QRS gives me QRS. So QRS is in the range of L with no restrictions on Q, R, and S. So the range of L is all of R3. The range of L is all of R3. Now, what is the dimension of the range of L? Well, this is equal to that. It equals to the dimension of R3, which is 3. The dimension of R3 is 3. Look at another one. L is a mapping from R3 to R3. It is a linear transformation defined by L of x, y, z is equal to y, x, 0. So we want to find range L. So let A, B, C be in the range of L. What could you take L of to get A, B, C? If you take L of B, A, anything, R. Well, when you take L of something, you switch the first two. That's why y is first and x is second, and the last one is 0. This is going to be A, B, 0. That is, if I want to take, you have to think. First, you have to realize the range of L is going to have 0 in the last entry. Now, if you want to get 3, 4, just try 4, 3, anything, 11. Okay, if you want to get RS0, anything, call it X. So I can take L of things and get things in this form. Now, personally, I think you're just going to have to see that. The best thing is to just see it. Just say, oh, the range of L is the set of all triples where the first and second can be anything. They don't even have to be the same as one another. But the third entry has to be 0. R and S are just real numbers. Now, of course, there are other ways of doing this. There are other ways of doing this. What you can do is you can write this second line using matrices. You can write the linear transformation using matrices. You can write this using matrices. You have a matrix. You want to multiply it by x, y, z, and you want to get back y, x, 0. Well, if you do 0, 1, 0, and you dot that with x, y, z, you'll get y. If you did 1, 0, 0, and you dotted that with x, y, z, you'll get x. And if you did 0, 0, 0, and you dotted it with x, y, z, you'll get 0. Okay. So now, well, we want is to see what we can get. We want to see, can we get A, B, C? Can we get A, B, C? That is, I want to solve this augmented system. A, B, and C. Okay? And you say, wow, you know what, I'm done. The first line tells me that y should be a. The second line tells me that x should be b. Now, if you want to switch these two rows to get it into perfect RREF form, fine. The third row, being all zeros to the left, tells me that c must be 0. C must be 0. Okay? So, what does this tell me? This tells me that A, B, C, to be in the range, must be y, b, 0. Y, x, 0. Okay, C must be 0. That's the bottom line. Okay? The range of L is the set of all yx zeros such that y and x are real numbers. Now, we do first figuring out what the matrix equivalent to this linear transformation. By the time you did that, you really should have, in this case, this simple case, you should have been able to just write down do three very similar problems, just in the time it took you to find the matrix. Then you have to reduce the matrix to this, find the solutions, and then you can answer it. But in the end, we got the same answers. Y and x are just letters. You know, I call them R and S up here, but they're just real numbers. Okay. Now, what is the dimension of the range of L? Well, there are two free variables, R and S. It's 2. I don't think it's best to solve it. To make up the matrix and see what ABCs you can get. Okay. Let us consider this next one. Let L, the mapping from R3 to R3, be defined by L of something in R3, call it x1, x2, x3. This is equal to 1, 0, 1, 2, 1, 1, 2, 1, 3 times x1, x2, x3. Okay? That is, I wrote the linear transformation as a product of matrices. And for the record, it's just x1 plus x3, 2x1 plus x2 plus x3, 2x1 plus x2 plus 3x3s. That is, L of this is equal to that. You don't even have to talk about matrices. But you were not given this. You were not given that. Bye-bye. The first thing we want to find out is L 1 to 1? Is L 1 to 1? We want to find the kernel of L. Is L onto? We want to find a basis oh my, for the range of L. Now, L is 1-to-1 if and only if the kernel of L is just the zero vector. But to get the zero vector, if and only if AX equals 0 implies that X is 0. Remember, L of X is the same as A times X. So if I want to know when this equals 0, that means I want to know when this equals 0. Okay? And this is, L is 1-to-1 only if that has to be the zero vector. That is, L is 1-to-1 only if that has to be the zero vector. But AX equals 0 implies X must be 0 is the same as the determinant of A is not equal to 0. Okay, think about this. Otherwise, you're gonna have to do a lot of work. So all I'm gonna do is calculate the determinant of A. Since it's just 3 by 3, I write down the matrix, and then for the fourth column, I put the first column. For the fifth column, I put the second column. And then spaghetti. 2 plus 1, oops, I am doing that backwards. Okay, 2 plus 1 plus 0. 2 plus 1 plus 0. 3 plus 0 plus 2. 3, which that is already, plus 2 plus 0. 3 minus 3 is 0. I get 2, which is not 0, which implies L is 1-to-1. L is 1-to-1. L is 1-to-1 if and only if the determinant of A is non-zero. Okay, so that one is done. That one is done. Okay, is L 1-to-1? Yes. Well, if L is 1-to-1, the kernel of L just contains the zero vector. Is L onto R3? That, now, let's talk about what onto means. You have the set V, you have the set W, you have some elements in W, you have some elements in V. This set is not onto because nothing went onto that element. This is not onto. Onto talks about the range W. Is L of something? Is it L of a value? Sorry. For every value in W, can you find an element in V that goes to each element in W. Can you find different? See, it sounds like English is not my strong point. It sounds like I want to find one element in V that goes to each element in W. No. For each element in W to be onto, for L to be onto, for each and every element in W. So V and W. For each and every element in W, it must be a V, like for this W, there must be an element in V that goes to W. And for to be onto, for the second element in V, something in W, for the second element in W, something must go to it from V. L of this element in V equals to that W. For this W, L of something goes there. For this W, L of something goes there. For this W, for this W, L of something goes there. This is onto. This is onto. Now, if this element also went here, it's still onto. Why? Because every element in W can be reached by something in V. This element, there were two in W, that element in W, there were two paths to get there. You can take L of this value, or you can take L of that value, and you get that W. You have to be able to take L of something to get the values in W. Now this mapping is onto, but is, and let's go to the left one. The left one is not even one-to-one, because I have two different elements going to the same element in W. Now, this one here is one-to-one. No, actually, it's not one-to-one, because this element in W, I have L of two different things that go there. So it's not one-to-one. So if you know it's one-to-one, it doesn't tell you anything about whether it's onto or not. If you know something about onto, it doesn't tell you anything about it being one-to-one. As an exercise, you should draw a mapping, draw a circle V, circle W, let it be onto. So do two cases, both where it's onto, but case one where it's not one-to-one, and case two where it is one-to-one. And then let it, do all cases. Let it not be onto. And then show an example, two examples where they're both not onto, but one is one-to-one and one is not one-to-one. Okay, is it onto? Okay. Now, the question is this. If I take 1, 0, 1, 2, 1, 1, 2, 1, 3, and I multiply it by x1, x2, x3, can I get anything I want in R3, like A, B, C? The answer is yes. This determinant determines this matrix was not 0. That is, if I call that A, and this X, and this B, remember, AX equals B, AX equals B has a unique solution if and only if the determinant of A is not 0. But wait a minute, wait a minute. We know the determinant of A is not 0. So AX equals B has a unique solution. I mean, I can tell you what the solution is. X1, X2, X3. It is what I take L of to get A, B, C is just this. is the inverse of this matrix times ABC. Remember, if on the left I multiply by A inverse, and on the left, on the other side, I multiply by A inverse, well, this is just X, and this is A inverse B. X is equal to A inverse B. And since A inverse is one matrix, and you multiply it by B, one column matrix, you're going to get one answer. This product is unique. X will equal that. So yes, is L onto? Yes. Now, let me answer. I really didn't write down a clean answer. I show the logic behind it. Okay, so this was an exam or something. A very nice answer would be the following. Is L onto AX equals B has a unique solution if and only if the determinant of A is not 0. But we concluded that the determinant of A is not 0. Hence, AX equals B has a solution for any B. Has a unique solution for any B. If and only if the determinant of A is not 0. Therefore, L is onto. Because I can put any value B. Remember, B is in R3. When you multiply A by X, you get something in R3. The question is, can you get everything in R3? Yes, if the determinant of A is non-zero. Okay, find the basis for the range of L. If we knew what the range of L was, then we'd have a fighting chance to find a basis. But the range of L is some subset of L. But if it's onto, we showed that we can get we can take L of different things and get everything in R3. The range of L is R3. They're exactly the same. They're the same set. So finding a basis for this set is the same as finding a basis for that. So I'm going to say R3, but I'm going to write this. A basis for R3 is 1, 0, 0. The natural basis is 0, 1, 0, 0, 0, 1. Have to have a very strong command on those two horizontal lines. Okay, so we answered everything there. Okay. Try another problem. I'm keeping the same questions, so I don't want to write them down again. Now, I do want to say something about the last problem, about how to find the range. And what you could have done was, you could have taken the matrix A. Remember, L of x was A times x, where A was 1, 0, 1, 2, 1, 1, 2, 1, 3. Now I want to know if I multiply it by x, which I called x1, x2, x3, can I get anything I want? Can I get A, B, C? The answer is yes, but more importantly, I didn't mean to say that. What you need to do is reduce this. Now, okay, you reduce it, you'll get the identity, you'll get different values here. That is, x1 will equal that value, x2 would equal that, and x3 can equal that. And L of, and then L of A prime, B prime, C prime would actually give you A, B, C, any arbitrary thing in R3. Now, again, the reason I know that this is going to work is because the matrix to the left of this line has a non-zero determinant, which means it will reduce to the identity matrix. And adding multiples of one of these to multiples of the others, you're just going to get a real number. Or, sorry, you're going to get a multiples of A, B, and C. I mean, maybe A prime would be 3A minus 2B plus 7C. And B might be 4A plus 3C. And C prime might be 2A minus 4B plus pi times C. Don't ask how pi is going to get there. But the bottom line is, we have it. We have x1 equals that, x2 equals that, and x3 equals that. And then I can get A, B, C. Okay, I hope that was clear. But you don't want to have to reduce it. It takes a while. Okay, so like I said, let's try another one like this. Let L be let L, the mapping from R3 to R3, be a linear transformation defined by L of x, y, z is equal to a matrix times x, y, z. Every linear transformation can be written down as a matrix times, in this case, x, y, z. Is L 1 to 1? L is 1 to 1 if and only if the determinant of A is not 0. And that's A. 1, 1, 2, 0, 1, 1, 1, 2, 3. Let us calculate this determinant. You could reduce it if you like. 1, 0, 1, 1, 1, 2. You get 3 plus 1 plus 0. 3 plus 1 plus 0. 4 minus 2 plus 2 is 4 plus 0. 2 plus 2 plus 0. You get 4 minus 4, which is 0, which implies L is not 1 to 1. Nice and cleanly. You don't have to go, well, L of xy, suppose L of xyz equals L of abc, and then show that xyz does not have to equal abc. Just look at the determinant. No. Now, the kernel of L is just the empty set. Sorry. The kernel of L just contains, kernel of L is just has a zero vector if and only if L is 1 to 1. But L is 1 to 1 means the determinant of A is zero. Is not zero. Okay. Now, these two statements are the same. But that one's not true in our case. The determinant of A is zero. That is, the kernel of L is more than the zero vector. You have to go, oh shucks. That means I have work to do. The kernel of L is more than the zero vector. In this case, we have a little work to do. I want to know that matrix times x, when that matrix times xyz gives me the zero vector. When is 1, 1, 2, 0, 1, 1, 1, 2, 3 times xyz, when does it give me the zero vector? Okay, I want to know when that gives me the zero vector. When this matrix, which I'm about to write, when this matrix times xyz, when does it give me the zero vector? That is, I want to solve for this. 0, 0, 0. I'll keep the first two rows the same. In fact, to be quick, I'll do row 1 minus row 2. 1, 0, 1, 0. So I got my 0 there already. 0, 1, 1, 0. And I'll do row 3 minus row 1 to kill off that 0. 1 minus 1, 2 minus 1, 3 minus 2, and 0 minus 0. Okay, the second and third row are the same, so I'll leave the first two the same, and the third row is going to become 0. Let's do row 3 minus row 2. This matrix is in RREF form. Column X, column Y, column Z. Z can be anything. It doesn't have a leading one. The second row says Y plus Z equals 0. That means Y equals negative Z. The first row says X plus Z equals 0. That means X is equal to negative Z. But Z is R. That's the kernel. This is, you can only take, so what can you take L of? That is, what can you multiply A by to get 0, 0, 0? The answer is negative R, R. That is R times negative 1, 1, 0. That is the kernel. The kernel of L is the set of all vectors. Now, you can write down R, negative R, R, or you can write it this way. I prefer to write it that way. Negative 1, 0. Such that R is a real number. Again, instead of this, you could have written down negative R. It is a typo here, I'm sorry. The last entry is R, so it should be 1. You can either write it down the way I circled it here, or instead of what I just circled, you could have put this instead. Negative R, R. That is the kernel of L. Now, is it onto? Is it onto? Well, I guess what we should have done was the following. Not only do I want to know is that what I multiply matrix A by to get 0, 0, 0, but I also want to know what I multiply matrix A by to get an arbitrary element of R3, namely ABC. So, sorry about that. What I should have done was also augment this with ABC, because I want to know when I can get, are there any constraints on ABC? Can I multiply A by something to get any ABC? Okay, so I am still going to do row 1 minus row 2, and I'm going to do row 3 minus row 1. I get 1, 0, 1, 0, A minus B. Row 2 did not change. Row 3, I do row 3 minus row 1. 0, 1, 1, 0, and I get C minus A. And then I just do row 3 minus row 2. And that goes to the third row. That is the first row. Did not change. The second row did not change. But now I do the third row minus the second row. The third row minus the second row. And this is what I get. This is what I get. First, when we read this, you always keep the matrix, the big matrix to the left, but the first time through to find the kernel, I'm just going to consider this matrix and that row 0. And we get what we get. I think we got Z was equal to R, Y was negative R, X is negative R. That implies that the kernel of L is negative R, R, where R is a real number. Okay? Now, and notice we ignored the last one. Now we're going to ignore this row of zeros. Okay? So, now I have a constraint here. I have a constraint. That last row says 0, 0, 0, 0 x plus 0 y plus 0 z is equal to c minus a minus b. I don't really care what the other two rows say. This tells me that c minus a minus b is 0. Bringing this over, it tells me that c must be a plus b. That is, I cannot just get any old a, b, c. I can get any a, I can get any b, but that last entry must be a plus b. So I can now write down the range of L. And write down the range of L. The range of L is the set of all A, B, A plus B's, such that A and B are real numbers. Now, we want a basis for this. Well, separate the A's and the B's. A, B, A plus B. Oh, it should be written as a multiple of A plus a multiple of B. And this vector and this vector will be the basis. Well, A is 1A plus 0 B's. B is 0 times A plus 1 times B. And A plus B is 1A plus 1B. You really should make sure that these underlying vectors not only span the range, but are linearly independent. And yes, they are. Okay. The only way this can ever equal 0, 0, 0, well, to get the top 0, B times 0 is 0. So you have A times 1, which is A, plus B times 0 is 0, is 0. That implies A must be 0. Now let's look at the second entry. Only one entry is a non-zero. We have A times 0, which is 0, plus B times 1, which is B, and this is supposed to equal 0. Well, 0 plus 0 equals 0, so B is 0. They're linearly independent. You should do a quick check on that. Okay, so now I have the basis. Okay. The basis for the range of L is 1, the vector 1, 0, 1, and the vector 0, 1, 1. Okay? That's the basis for the range of L. And that was all the questions on that one. If you're taking a real linear algebra class, you are going to see this problem on the test. It's not a watered down course. You will see that problem. Okay. Suppose we have this one. Let L from R4 to R3 be a linear transformation defined by the following. L of A1, A2, A3, A4, which is something in R4, it is equal to A1 plus A2 comma A3 plus A4 comma A1 plus A3. One kind of basis for the range. Find a basis for range L. So first we should find range L. First we should find range L. Okay. So I want to write this as a matrix. Something times A1, A2, A3, A4, and it's supposed to give me this. A1 plus A2, A3 plus A4, and A1 plus A3. So I want to get 1A1 plus 1A2. So I'll put a 1 and a 1. This one gets multiplied by A1. This one gets multiplied by A2. and the other two entries are zeros. Now I want to get A3 plus A4. So I want the third position to be 1 because it'll get multiplied by the third position in the column vector. I want the fourth position to be 1 because it'll get multiplied by A4. So far we have 1A3 plus 1A4. No A1s and no A2s. I want A3 and A4. The first column I put a 1, in the third column I put a 1. The others I put zeros. That is the matrix. Okay, this is the matrix. And we want to find the range. I want to know, what kind of values this can equal. What kind of values it can equal. That means I take the matrix and I augment it with x, y, z. Are there any constraints on x, y, and z? I will do row 1 minus row 3 for the last matrix. Actually, I have row 1 minus row 3. Row 1 minus row 3. So the first row does not change. The second row does not change. 1 minus 1, 1 minus 0, 0 minus 1, 0 minus 0, x take away z. Okay, now I will do row 1 minus row 3 to get that to be a 0. And of course I run out of space. So we come up here. Okay. And row 1 minus row 3. 1 minus 0, 1 minus 1, 0 minus a negative 1, 0 minus 0. X take away x minus z is z. The second row did not change. The third row did not change. Maybe I'll interchange the second and third row. 1, 0, 1, 0, z. 0, 1, negative 1, 0, x minus z. 0, 0, 1, 1, y. I'm going to use the third row to get zeros in these two positions. I'm going to do row 1 minus row 3, and I'm going to do row 2 plus row 3. Okay. Row 1 minus row 3 is 1, 0, 0, minus 1, z minus y. I add the last two rows, x plus y minus z. I don't do anything to the last row. This was A1, A2, A3, and A4. A4 can be anything. The first row tells me that A1 minus A4 is equal to that. So A1 is equal to A4 plus z minus y. The second row tells me that A2 plus A4 equals that. That is A2 minus A4, which is R, plus X plus Y minus Z. And the third row tells me that A3 plus A4 equals Y. That is A3 is equal to negative A4 plus Y. The bottom line is I'm able to get anything in R3. I'm able to get anything in R3. Let me show you how this is true. Suppose I want to get 3, 4, 5. Suppose X, Y, Z is 3, 4, 5. Well, R is R, and we have Z minus Y. 5 minus 4 is 1. And X plus Y is 7, minus 5 is 2. So I got negative R plus 2. And here I get negative R plus 4. And A4 can be R. Okay. So if I let R be 0, 1, 2, 4, 0. See if I'm right. L of one, 2, 4, 0. Well, first I should add A1 and A2. 1 plus 2 is 3. And then I'm supposed to add 3 and 4. 4 plus 0 is 4. And then I'm supposed to add 1 and 3. 1 plus 4 is 5. Yeah, I got 3, 4, 5. Now, it says, believe it or not, that R can be anything I want. Well, what if R was 1? So, if R is 1, let's see what we get. Let's see if it really works when R is 1. Well, 1 plus 1 is 2, so A1 is 2. Negative 1 plus 2 is the same as 2 minus 1, which is 1. And negative 1 plus 4, better known as 4 minus 1, is 3. And 1 plus 0 is 1. Well, I'm supposed to add the first 2. 2 plus 1, look at that, it's 3. Then I'm supposed to add the third and the fourth. Look at that, amazing. 3 plus 1 is 4. And then I'm supposed to add the first and the third. The first and the third. 2 plus 3 is 5. I can get anything. Okay. So now, I didn't really finish writing it up. I wanted to show you that it actually works. Now, some stuff somehow got erased, so let's put it back. What I put here on the right side, that was kind of my side work to make sure that it worked. But the bottom line is, I found what x1, x2, x3, and what a1, a2, a3, and a4 should be to get any x, y, z. In other words, I started with the following. I started with the matrix 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, and I asked myself, what can I multiply it by? what can I multiply it by to get an arbitrary x, y, z? And the answer was, there's no constraint on what I can get for x, y, and z. There was no constraint. Because whatever r is, I can add z and then take away y. I can calculate x plus y minus z and add that to negative r. And I can compute negative r plus y. And I can compute a value for r. That is a1, a2, a3, and a4. There were no constraints on x, y, z, x, y, and z. All right, so the range of L is R3. It's R3. Well, that's enough for me. So then a basis for the range of L is just a basis for R3. And you have to know a basis for R3 without doing much work at all. In fact, you should just be able to write it down. That sometimes, okay, so we'll do it here. The basis for the range of L, code, basis for R3 is, use a natural basis. 1, 0, 0, 0, 1, 0, 0, 0, 1. First, before you find the basis for the range of L or for the kernel of L, first find the kernel of L. First find the range of L. Then decide what the basis is. Once I knew what the range of L was, it was just R3 is a piece of cake. I wrote down a basis for R3. Of course, there'd be nothing wrong if you wrote E1, E2, E3. Unless your teacher said otherwise. Okay, they mean the same, but some teachers may say, you know what? Maybe they don't know what E1 is or what E2 is. I want you guys to write it out. Okay, we have a nice little theorem here. A very powerful theorem to make life a little bit easier. L, the mapping L from V into W is a linear transformation of a n-dimensional vector space V. So the dimension of V is n into a vector space W. Then the following is true. Then the dimension of the kernel of L plus the dimension of the range of L is equal to n. That is, it is equal to the dimension of V. And we're not going to prove that. The proof is fairly straightforward. I know how to prove it, but it's not worth the trouble. There are two corollaries to this theorem on top. these will prove. Let L, the mapping from V to W, be a linear transformation with the dimension of V. This is important. Let me write it on one line. With the dimension of V equaling the dimension of W. Then, if L is onto, then L is 1 to 1. And B, if L is 1 to 1, then L is onto. That is, L is onto if and only if L is 1 to 1. Now, let us just write it down that way. Give me another line. L is onto if and only if L is 1 to 1. Okay. Suppose L is onto. That means the dimension of the range of L is equal to the dimension of V. Okay? But the dimension of V is n. It says n-dimensional vector space V, which is equal to n. Okay, now we know that the dimension from the theorem above, the dimension of the kernel of L plus the dimension of the range of L is equal to the dimension of V. Okay, we don't know the dimension of the kernel of L yet, but we know the dimension of the range of V. The dimension of the range of V is n. And it equals to the dimension of V is n. Therefore, this must be 0. 0 plus n equals n. The dimension of the kernel of L is 0, which means the kernel of L is just the 0 vector, which implies L is 1 to 1. So, if L is onto, I showed L is 1 to 1. Now let us suppose that L is 1 to 1. Let us suppose that L just happens to be 1 to 1. Doesn't have to be 1 to 1, but what if it is? Suppose L is 1 to 1. That means every element in V goes to just one and only one element in W. Well, that would mean the dimension of V is the same as the dimension of the range of L. But the dimension of V is n. The dimension of V is n. Okay. so we want to show it's onto. Well, but this is equal to the dimension of W. This is equal to the dimension of W. Okay. Well, that's going to show that it's onto. That's going to show it's onto. The dimension of the range and the dimension of W are the same. They both equal N. So L is onto. They can have different dimensions and be onto. The dimension of V to be onto, the dimension of V and W must be the same. Okay. I'm gonna end the video right here. Thank you.